Hello, I'm Sylvia Knight, Head of Education at the Royal Meteorological Society. In this series of short films, we're covering some of the background information that geography teachers may find useful if they're teaching weather and climate at secondary level. This is linked to the Weather and Climate Teaching Guide with accompanying classroom resources which you can find on our website, MetLink. In this film, I'll be looking at what makes the climate in an urban area, whether that's a town or a city, different to the surrounding countryside. Urban areas can have an impact on their climate. Sunshine duration can be 5 to 15% less in urban areas compared with rural locations. The humidity is lower, particularly in summer, but precipitation is higher, at least of rain. The number of snow days is lower. It can be up to 10% cloudier, and fog can occur twice as often in winter. The annual mean temperature can be 0.1 to 1 degree Celsius warmer, with the winter maximum temperature being up to 2 degrees higher. And you can have 2 to 3 weeks fewer occurrences of frost. An urban heat island is a metropolitan area which is significantly warmer than its surrounding rural areas. The temperature difference is usually larger at night than during the day and is most obvious when winds are weak and the sky is clear overnight. One of the main causes of the urban heat island is the fact that there is little bare earth and vegetation in urban areas. Less of the sun's energy is reflected and more heat is stored by buildings and the ground in urban areas. The heat generated by heating, cooling, transport and other energy uses also contributes, particularly in winter, as does the complex three-dimensional structure of the urban landscape. Water is constantly being lost from bare earth through evaporation and from all sorts of vegetation through evapotranspiration. These processes, together with subsequent condensation in the atmosphere, moves energy from the surface of the earth up into the atmosphere above. In rural areas, there tend to be more lakes, ponds, streams, rivers and vegetation. Also, when it rains in urban areas, water tends to be quickly channeled into underground drains and sewers and is not left on the surface to cool it down. The lighter or shinier a surface, the more of the sun's light gets reflected straight back out to space. Many urban surfaces are very dark, tarmac, roofs and things like that, so less of the sun's energy tends to get reflected than in rural areas, although it depends a lot on what sort of rural environment you're looking at. Sand and water are much more reflective than thick woodland. Albedo is measured on a scale of 0, no energy is reflected, to 1, where everything is reflected. Any of the sun's energy that isn't reflected back into space is absorbed, heating the surface up, so the lower the albedo, the warmer the object will get. This daytime infrared image of a street in Melbourne in Australia clearly shows how much more the dark coloured road surface has warmed than the lighter coloured buildings. To make matters worse, many buildings are designed to store heat. Insulation means that once they warm up, it's very hard to cool them down at night. The complex three-dimensional structure of the urban landscape means that they're less well ventilated than rural areas. So in this diagram, you can see a summary of the difference in the ways heat is transported between rural and urban areas. Towns and cities don't heat up the same amount everywhere. The more densely built up an area is, the more it heats up. AstroTurf is one of the worst surface materials with the greatest potential to generate an urban heat island. In this image from a primary school in Greater Manchester on a warm but not particularly hot day, you can see that the AstroTurf has warmed even more than the black tarmac next to it. And on this graph, you can see that the fine scale features can be very important. A small local park can reduce the local temperature by a couple of degrees. And in this fairly old temperature map of London showing temperatures one summer night in 2000, the impact, for example, of Richmond Park is very clear. These results were collected by a Royal Met Society schools experiment in 2009. It shows a difference in temperature around Manchester categorised according to land use type on a night with a well-developed urban heat island. The grey bar shows the mean temperature recorded for each land use type. The line indicates a measure of uncertainty in that measurement. The precise weather conditions do matter. Sometimes rural areas can be warmer than the city in the middle of the day. The urban heat island dissipates rapidly at sunrise and develops rapidly at sunset. It's the rate of cooling after sunset that sets up the urban heat island, as well as the rate of heating after sunrise, as we can see in this graph, which shows the development of Birmingham's urban heat island on the night of the 22nd of July 2013, which was during a heat wave. NASA researchers studying urban landscapes have found that the intensity of the heat island created by a city depends on the ecosystem it replaced, as well as the regional climate. Urban areas developed in arid and semi-arid regions show far less heating compared with the surrounding countryside than cities that were built surrounded by forested land and temperate climates. So to summarise, the urban heat island effect is biggest in a large urban area, when there is an anticyclone or high pressure conditions which give you those clear skies and very light winds, at night, just before sunrise, in the summer, although this does mean that the night is shorter and so the conditions persist less long, and when the weather conditions don't change through the night, and then in a city which replaces forest in a temperate climate. Urban heat islands can have important consequences for which areas are most badly affected by fuel poverty. Also, the growing season can be up to 15 days longer in an urban area. So what effects do urban heat islands have on measurements of climate change? Although most of the really long temperature records available to meteorologists come from in or near urban areas, the weather stations tend to be found in parks and open spaces which are less affected by changes in urbanisation. One study has attempted to see how much the urban heat island effect has affected long-term temperature records by comparing the temperature records recorded on calm nights, when there is a big urban heat island effect, with those recorded on windy nights, when there is less of an urban heat island effect. The study suggested that the long temperature records were not affected by the urban heat island. In other words, any long-term trends in temperature seen in the records were probably the same as if they had been recorded in a rural area. In the last few decades, data from satellites has been added to the records available to meteorologists. And so the IPCC concluded in their 2007 climate change report that the effects of urbanisation and land use change on the global temperature record are negligible, less than 0.006 degrees Celsius per decade over land and 0 over the ocean, as far as hemispheric and continental scale averages are concerned. All observations are subject to data quality and consistency checks to correct for potential biases. The real but local effects of urban areas are accounted for in the land temperature data sets used, both by excluding as many of the affected sites as possible from the global temperature data and by increasing the error range. Urbanisation and land use effects are not relevant to the widespread oceanic warming that's been observed. In urban areas, tall buildings and generally rougher land surfaces have an effect on the flow of air, altering the course of the wind and producing turbulence. Turbulence causes airflow patterns to be complicated rather than straight or aerodynamic. Even a simple building can produce a complex airflow pattern. This flow of air can in turn have an impact on the transport and concentration of pollution and rubbish. This is a simplified diagram showing how air is redirected around a building. In front and to the sides, there will be faster airflow on the ground. In high wind conditions, this could be a problem. The swirling airflow, turbulence, in some places means that pollution and any litter will tend to end up getting trapped there until the wind changes direction. Flow along streets is even more complicated than flow around a single building. Depending on how high the buildings are and how wide the streets are, the airflow will be different, and it depends on the street orientation and wind direction. A lot of UK towns and cities have parallel rows of streets. The airflow has consequences for the dispersion of pollutants. Are they getting trapped in pockets? Are some areas of housing going to be particularly unhealthy because of where exhaust fumes end up? On the dispersion of heat, particularly in the summer. And pollution has always been an issue for cities, and how the flow of air in the urban area redistributes and removes it. Smogs were common in many British cities in the late 19th and early 20th centuries, when domestic fires, industrial furnaces and steam trains were all burning fossil fuels and emitting smoke and other hygroscopic pollutants. The smogs were particularly bad during the winter months and when temperature inversions built up under high pressure, causing the pollutants to become trapped in the lower atmosphere and for water vapour to condense around these particles. One of the worst of these pea soup fogs was the London smog of the winter of 1952 and 1953. Approximately 4,000 people died during the smog itself, but it's estimated that 12,000 people may have died due to its impacts. As a result, the Clean Air Act of 1956 was introduced to reduce these emissions into the lower atmosphere. Taller chimney stacks and the banning of heavy industry from urban areas were just two of the measures introduced, and consequently fewer smogs were recorded in the UK during the 60s and 70s. Research in the 1990s, however, showed that another type of smog, photochemical smog, is now occurring in urban areas as a result of the fumes from car exhausts and the build-up of other pollutants in the lower atmosphere, which react with incoming solar radiation. The presence of a brown-coloured haze over urban areas is an indication of photochemical smog, and it can lead to people experiencing breathing difficulties and asthma attacks. People living in urban areas with poor air quality were more susceptible to fatality from the 2020 coronavirus pandemic. A 2016 letter to Nature journal suggested that the public is increasingly aware of the health and economic costs of air pollution. Poor air quality is linked to over 3 million deaths each year worldwide, and 96% of people in large cities are exposed to pollutant levels that are above recommended limits. The costs of urban air pollution amount to 2% of GDP in developed countries and 5% in developing countries. Media attention and the increasing availability of data are reinvigorating efforts in many countries to tackle air pollution, driven as much by local and national politics as by the science. In response, startup companies are rushing to produce cheap air monitoring sensors costing hundreds rather than tens of thousands of pounds. Such devices bridge the gap between sparse government measurements and individuals' wishes to track their personal exposure. The devices typically measure particulates, sulfur and nitrogen oxides. However, the devices are rarely calibrated to the location and time when they're being used, so at best they can be used to raise awareness of pollution rather than give accurate and absolute readings. The greater presence of cloud condensation nuclei over and downwind of urban areas can lead to cities being wetter and having more rain days than the surrounding rural areas. It was often said, for example, that Rochdale had significantly smaller amounts of rain on Sundays when the town's factories were closed. However, you could also argue that on days when there's less pollution and therefore fewer condensation nuclei in the air, you end up with fewer and therefore larger cloud droplets, which are more likely to fall as rain. So another study suggested that the driest days in Manchester are Wednesday to Friday. However, other factors play a major role, especially heat islands. These can enhance convectional uplift, and the strong thermals that are generated during the summer months may serve to generate or intensify thunderstorms over or downwind of urban areas. Storm cells passing over cities can be refueled by contact with the warm surfaces and the addition of hygroscopic particles. Both can lead to enhanced rainfall, but this then usually occurs downwind of the urban area. A 2019 study suggested that mean precipitation is enhanced by 18% downwind of the city, 16% over the city, 2% on the left and 4% on the right with respect to the prevailing storm direction. City planners can use computer models to see how the air flows and to help plan future developments. Many city authorities are now investigating or implementing devices to improve the urban microclimate. For example, by painting buildings and pavements light, shiny colours that can enhance the reflection of light and emission of heat. Some paints combine a reflective base coat with a darker pigment and could reduce air conditioning use by over 30% and cool cities by 2 degrees. However, the surfaces do have to be kept clean. Similarly, cool pavements and roads reduce the heat island effect, whilst also giving lower tyre noise and better nighttime visibility. On a hot summer day, the surface of a green living roof can be cooler than the air temperature, while a rooftop without plants can be warmer. Green roofs can give a 70% reduction in air conditioning costs for a one-storey building, reduce flooding, reduce air humidity, insulate in the winter, reduce air pollution, provide a habitat for wildlife, and just generally be a nice place to be. The stronger the roof, the bigger the plants which can be grown. Sedum is the one that's most commonly used. Large trees on the south or west of buildings can reduce air conditioning costs by 30%. Urban trees provide air temperature reduction through evapotranspiration and increased albedo. They can reduce building energy use, they can increase absorption of UV, they can improve the water quality, reduce noise, and improve human comfort and well-being, as well as increasing property value and just generally being aesthetically nice, as well as improving community cohesion. Several cities, including Chicago, for example, have tree planting programs. These infrared images from an early years playground show the dramatic difference in temperature between a willow arch at 19.2 degrees and black tarmac at 44.6 degrees, and that was on a day when the sun wasn't even shining. Water features can also have a significant impact on local temperature because of the cooling impact of evaporation, as well as the higher heat capacity of water. Urban areas are particularly vulnerable to changes in the climate, and as the world becomes increasingly urbanised, more and more people will become vulnerable to changes in climate and extreme weather events. London was up to 9 degrees Celsius warmer than surrounding areas during the 2003 heat wave, and there were 600 heat-related deaths. Heat waves like that of 2022, when London's fire brigade had its busiest day since World War II because of heat-related fires, are expected to become more common in the future. They will happen on average every other summer by mid-century, and if global emissions remain high, later this century those temperatures may constitute a cool summer. Given the long lifetimes of buildings and urban areas, we need to plan urban areas now to anticipate the summer temperatures of the future. There are many useful sources of data, maps and other information about urban climates, some of which we've given in the text below. And in the next film, we'll look at tropical cyclones, known in some places as hurricanes or typhoons.